This meeting is being recorded.
Great, thank you, Daniela. All right, as always, I'm just going to give a brief explanation for anyone who might not know of the SAGE journey. SAGE is a program whose mission is to inspire and encourage students to explore STEM careers in the future. We do this by offering free summer camps, paid internships, professional growth sessions, and many opportunities to connect with professionals who care about you and your future. SAGE Live is part of the SAGE journey. It's an online gathering of students who have attended or applied to a summer camp and are curious about the next stages of their SAGE journey. It's also a time to reconnect with SAGE volunteers. It's held monthly via Zoom between the months of September and May, and topics covered are relevant to your journey, whether it's career related, such as designing your life, resume workshops, or preparing an interview, or new and exciting topics such as quantum computing, AI, machine learning, and, as we're going to hear about today, accelerators. Today we have two guests from two national labs, Oak Ridge National Lab and Los Alamos National Lab, and they will share what kind of accelerator they have and the cool science you can do with it. Please feel free to join the conversation by asking questions in chat. Or by unmuting yourself to speak. I think both speakers said that they're okay with getting questions during the presentation, so you don't have to wait till the end. All right, our first speaker today is Dr. Kirsten Runsard, and she works at Oak Ridge National Lab, started working as a Shull Fellow in 2018. She's currently a staff scientist in the Accelerator Physics Group in the Research Accelerator Division, Neutron Science Directorate. She holds a grant through the DOE Early Career Research Program that supports measuring high dimensional ion beam distributions and improving simulation models at the SNS beam test facility. She got her PhD from the University of Maryland, College Park, and her bachelor's from Rutgers University in 2012. And so, Kirsten, take it away.
All right, great. I'll start sharing my screen. Thanks everyone for being here. And apologies in advance, I got a little bit of a frog in my throat, was recovering from a cold this week. So sorry if I have to cough once or twice. Anyways, thanks Andrea for the introduction. Like Andrea said, I'm going to be talking to you today, giving you a tour of our accelerator that we have here in Tennessee. It's called the Spallation Neutron Source. And as my job title suggests, I'm going to be focusing a little more on the accelerator end and taking us on a tour of the accelerator and talking about all the cool technologies that make the accelerator work. And I think Shay is going to be telling us a little more from the uses end and the sorts of things you can do with accelerators for science. So just to situate us, we're East Tennessee, so Oak Ridge National Lab is located sort of between Nashville and the Great Smoky Mountains National Park, right between this little valley area between the Cumberland Plateau and the Appalachian Mountains. It's very green right here. Our logo is the oak leaf because we have a lot of oak trees, as the name might have tipped you off. So I work at Oak Ridge National Lab. This is a bird's eye view of the lab. So let me get my little pointer out. So this is the main part of the campus. This grew up around this historic reactor that's no longer operational, the graphite reactor. This was part of the Manhattan Project. It was built during World War II and contributed to the building of the nuclear bombs that were used near the end of World War II. So after World War II, the lab didn't shut down, but scientists found other ways to use these facilities. So the reactor kept running until 1963 for various peaceful scientific missions, and the lab has just grown ever since. So I have these two other sites marked out, one slightly to the north of the main campus, which is the Spallation Neutron Source, what we'll talk about today. And slightly to the south is high flux isotope reactor. So these are two sites where we produce neutrons for science in two very different ways. Zooming in on those two sites, so that's a fun sound. So the high flux isotope reactor creates very bright neutron beams. This is a continuous source of neutrons, so it's always sending neutrons to the experimental areas. The SNS the accelerator produced neutrons are a little bit different. They come in pulses. So these are very bright pulses of neutrons. We're delivering pulses of neutrons 60 times per second to users. And so it allows different types of measurements. Some measurements that take advantage of that timing might use the SNS, some experiments that care more just about the total number of neutrons and getting very bright source of neutrons might go down to the reactor. So we can serve a lot of experiments between these two facilities. This is a close-up of the SNS site. They always take the photo from this angle, which I think is a shame because the accelerator is actually like the furthest thing away from you in this photo. So the accelerator footprint I'm tracing right now with the laser pointer. So we start the beam all the way back here at the very top edge of the photo. We go through a linear portion of the accelerator. It's buried underground. You can't see it. So this is done for safety. Accelerators tend to emit some amount of radiation. So we like to bury them under dirt. It's perfectly safe to walk around on the top of this berm. Makes a 90-degree turn, circles this little square building about 1,000 times, and then shoots off to this building that looks like it's kind of looks like 3 long buildings shoved together. And this is our main target and experimental hall where we do neutron science. This very cool looking curvy building has nothing to do with the accelerator. Some people call this the banana. It's where all the scientists and people who work on the accelerator sit. So we employ neutron scientists at Oak Ridge, but we also serve a large user community. So we have people traveling from all around the country and all around the world to come for a period of time, maybe a couple of days, maybe a week or so, to do experiments in our neutron hall. So that this little building at the very bottom of the screen is it's like a little hotel. So people will come, stay on site while the accelerator is running, and come try to get their data, and they're allocated a certain amount of time to use our facilities. So as you imagine, we do a ton of different experiments, whatever someone can think up to do, they can come here and try it. I do see a question in the chat. What are the benefits having 2 different portions in the accelerator, linear and circular? You're going to hear way more about that than you probably wanted to. So I'll ask it again if I haven't properly addressed your question by the end. All right, so now we're gonna get to that, going through a tour of how the accelerator facility works. This is a little flyover video that gives an overview of the path that particles take through the accelerator. So the basic job of the accelerator is to put protons on the target that's in that target hall and create neutrons. But as you'll see, there's a very long path to get there. So we're going to start all the way in the back here. This is called the front end. This is where we birth the particles. We're birthing negative hydrogen ions, and we'll get to why in a second and how we do that. But as you'll see in a second, there'll be a little fuzzy dot representing a bunch of ions will come out of this front end. And it travels down this long straight section. This is called the linear accelerator. And this is what actually does the work of acceleration. So this brings the beam up to 1 GeV, which is about 90% the speed of light. So every meter along this about 300-yard, 3 football field long linear accelerator makes the beam go a little bit faster. And then this ring part, it's called an accumulator ring. Its job is to make our pulse of ions as bright as possible. So you see it's designed so that every time a bunch comes down the linear accelerator, it stacks on top of the last bunch. So this way we build up a very, very bright bunch of ions, peel that off, send it to the target hall. It interacts with our target and makes a very bright pulse of neutrons. And then these rays are all the neutron beamline experiments. And the little yellow shapes at the end of them are the sample environments and the detectors that are used in the neutron experiments. So we're going to step through in a little more detail all these parts of the accelerator, starting, following very logically the path of the ions. So at the front end, well, I'd say we start with an ion source, really start with a bottle of hydrogen gas. We fill a chamber with this hydrogen gas, and then we pump in electrical energy through the form of an RF antenna that heats up the gas and causes it to form a plasma. So this is actually a picture of the inside of our ion source. Sorry, that's my phone that's making the weird noise. That over there. So this round thing that's got about 3 turns in it is the RF antenna. It's acting kind of like a microwave, but instead of heating up food, it's heating up this gas and causing it to form a plasma. In this case, the plasma glows this pinkish purple. So we're starting with hydrogen, which is the simplest atomic structure ever. It's just a proton and an electron. In heating it, mostly what happens is we dissociate that electron from the proton. So you have a separated electron proton plasma. That's what happens to most of the hydrogen atoms. Some of them, however, actually snag an extra electron, and so they become a negatively charged ion with 2 electrons. And we've actually done a lot of engineering to make sure that we get to promote production of this H- negative hydrogen ion. It's a little bit harder to do this. There's a really good reason that I'll get to in a second, but basically we want H- in our LINAC. So we want to be accelerating H-, not H+. So we've designed it so the H- favorably forms near the opening of the ion source and gets sucked out and then accelerated down the LINAC. So the LINAC is all about getting up to speed. So every meter you're trying to pack as much energy gain into that ion beam as you can. About the first third is based on some pretty old technology, sort of emerging from the 1960s or so. These copper-based cavities is a picture in the LINAC. It does look like just a bunch of tubes with other tubes coming out. But inside this copper structure, we have resonant cavities that are shaping the we're pumping in electromagnetic fields. We're shaping those fields so they tend to give particles a boost in the right direction. This is a little diagram of what a cavity can look like. So it's a hollowed out, it's a metal surface that's hollow in the middle. You can think of it almost like an instrument, like a guitar cavity is the body of a guitar. If you pluck a string, the sound resonates and you shape the guitar cavity to make a nice sound. Here we're actually resonating electromagnetic energy and we're shaping the cavity to give us that favorable mode that gives us acceleration to the ions. So we already entered pretty fast into this LINAC, but by the time we come out of this first third, we're at about 55% the speed of light. Then we enter the superconducting section of our cavity. So this was an exciting aspect of the SNS. It was the world's first. This technology had been applied to electron beams before, but not to proton LINACs. So this is the first superconducting proton LINAC. The technology is a little bit more complicated. So in the picture you see down here, these little green balls are the ions traveling through the accelerator, and you can see they're inside this cavity. But then these cavities are wrapped in what we call a cryomodule, and that's filled with liquid helium to keep the temperature of these cavities at just 2 degrees Kelvin. So it's 2 degrees above absolute zero, or about negative 458 degrees Fahrenheit. Why do we want it so cold? Because superconducting materials. So superconducting materials are metals that have this special property, which is when you get them cold enough, all the electrical resistance disappears. So most devices, the copper wires in your house, when you charge your phone or your computer, there is resistance. This usually appears in the form of waste heat. So that's why electronics sometimes get hot when you use them or charge them. And this can reduce the efficiency. So superconducting materials allow us to get to higher efficiencies due to the fact that they have a special property of no resistance when they're cold enough. So we can get higher fields. We can get slightly more power efficiency with these superconducting cavities. So this does actually allow us, our LINAC is a little bit shorter than if we had used copper cavities the whole way down. So this was a bit of a risk they took when designing the accelerator that really paid off. And by the end, we're going at 1 GeV, about 90% the speed of light with our H- ions. Just little sense of scale. So we do put 1.4 megawatts of power on the target when we get to the end here, but actually running this facility, and particularly the LINAC, takes just under 30. I heard about 26 megawatts of power. And this is enough to service a small town. So it's actually a little bit more than the town I live in uses for the whole town. To run the accelerator. All that power's got to come from somewhere, and we can't exactly just plug it into a wall the way you do with things at home. So there's a whole building not shown on this diagram that runs the whole length of the Linac that has all the infrastructure to convert power from the form that the power company sends it to us into the pulse form that we need to run our linear accelerator. So it's a long gallery of these vertical tubes are called klystrons. They're amplifiers. When this whole building is about supplying all the power that eventually gets put into the beam to make it go fast. And the largest power source we have in this building is equivalent to running 5,000 microwave ovens at the same time. So that's where your 30 megawatts, some of it is going. So next we go into the ring, and remember the job of the ring is just to pack all that power on top of itself. So every pulse gets stacked on top before we send it to target so we can make the brightest pulse possible. And so there was a little bit of engineering that had to go into how do we bring two beams together. So it's sort of like merging traffic on a freeway. You've got the incoming beam coming one way and the beam that's recirculating in the ring coming the other way. And this is the whole reason why we wanted H-, why I went to extra work at the beginning of the Linac to make H-. So particles bend in a magnetic field, and the direction they bend is determined by their charge. So what we do is we have protons in the ring. Remember, proton is the positive ion of hydrogen gas. And then we have H- coming in from the Linac, and so they sort of dovetail together. And so right at the point of injection, we want to convert the H- coming from the Linac to a proton beam that's in the ring. It's pretty easy to take those electrons off. You really just need to pass through a material. So we put a very thin carbon foil, and that does the stripping of those electrons. And this is very tiny, and this is a huge facility, but this comes down to this foil you could hold in the palm of your hand. It's a very, very thin, very small, but very important piece of the whole facility. That's what it looks like before we put in the accelerator. This is what it looks like when we take it out. So it definitely, this is a very powerful beam that damages things as it hits them or passes through them. So that's just from heat. Some of the heat from the beam actually transfers into this material and melts it a little bit, but it still strips. As long as we don't put a hole in it, we're good. But we do change these out, not super frequently, but it's a regular part of running that we can change these out as needed without interrupting the beam too much. So we go around that ring about 1,000 times, stacking more particles on top, and then we send it to target. So we peel off and go to the center of this target hall. We make neutrons through a process called spallation. That's this little diagram here. So we take a material with a high atomic number. So for us, we use mercury, and I believe the atomic number is 80. We also want it to be neutron rich. So the most common isotope of mercury has, I think, 122, something like that, neutrons in that nucleus as well. So a high energy proton hits the nucleus and causes it to spallate off some small fragments that are just individual neutrons. And this is a pretty high efficiency process. So for one proton in, we get about 20 to 30 neutrons off of a single nuclei. And that's our job. We want to make as many neutrons as possible so that the experimenters get good statistics and they don't have to run their experiments as long. So more neutrons generally means the experiments run faster and easier. This picture here is what the target actually looks like. So another property of mercury is that it's liquid at room temperature. So this was a design choice. So if you can imagine the damage that foil took, now you're trying to take 1,000 times that much power and put it on a single target. So the nice thing about liquids is that you can't crack or damage them as easily. And they also, this mercury is continuously flowing through this path like this through this target. So it's conducting the heat away as well, carrying the heat away. So the yellow balls are protons and the blue are neutrons kind of coming out in every direction around this proton, around this target. But it's really getting a beating. So each pulse of beam, remember, doing this 60 times per second. Each pulse is equivalent to throwing a 16-pound bowling ball at 150 miles per hour. Or it's like blowing off a stick of dynamite 1 time per second. So it's a lot. And this was definitely one of the trickier parts of the whole accelerator facility to get right. So we do change these out about 3 times per year right now. We're trying to move down to 2 times per year. But this is a usable piece. Eventually it will damage and break, and we don't want that. So we change it out. But it did take a little bit of engineering to figure out how to get it to last a full run cycle, which is up to a couple of months. And then here we have this. This isn't really a critical piece of infrastructure like everything else I showed you. It's just really cool to show. This is the remote handling system for the target. So high power ion beams, if you put them anywhere, you will cause radiation if they interact with materials in the environment, like that foil, like that target, or if they accidentally hit the beam pipe wall. So we have some very radioactive parts of the accelerator that aren't safe to go. The target is one of them. Once you've used a target, nobody's touching that thing or getting too close to it. So we do have these cute little robot arms that come in and are used to extract the target, move it, and help install the new one. So that's the accelerator facility in a nutshell. I did want to touch on a little bit how we run the accelerator. This is a overview of the central control room. So this room is staffed 24/7, even when the accelerator is not running. But when it is running, there is always at least 3 operators here who are just keeping an eye on things. It can be really quiet here if everything's running exactly as it should. It can be really frantic here if something's broken, and it's their job to figure out what is it, how bad is it, who do we need to call to come get this fixed. If you're a systems expert, you might get called in the middle of the night to come fix the thing that you're an expert in. But they're sort of the ones who are always keeping an eye on things. This is staffed even when the accelerator is down. So we usually run for a couple of months, we'll run, and then we'll go down for a month or 2 for maintenance, just to check things out, to do some necessary upgrades. If things were broken, we'll get in there and fix it then. And so they also keep track of what's being fixed, and is anyone going down into the accelerator tunnel underground, and how long are they going to be there, and what are they doing while they're there. So pretty much all the work on the accelerator gets communicated through this control room. Little cartoon of what it's like to be an operator. So like I said, sometimes quite frantic. Sometimes you're sitting there all night and things are running great and it's really boring. Those are good nights. Here's a picture of the control room back when they first started the SNS up, getting the first beam to target, making those first neutrons. So there's not usually this many people in the control room, and they don't always look this excited, but this gives you an idea of all the people who, were not only there because they were being curious, but were there because they were ready to step in and help out, because this is such a complex system that not one person knows all of it. So they're all there to weigh in if what they're an expert in, was the key. Starting up an accelerator never goes smoothly. So lots of people on board waiting to help out if they can. So that's the accelerator. I did want to touch a little bit on what we actually use the accelerator for. That's a lot of work, so you better hope that we're doing something good with it. I like to think of an accelerator as a cross. It's sort of like a microscope meets an X-ray machine. So these neutrons, when you put something in front of that neutron beam that we make in the target hall, it's sort of like a microscope because the neutron can see and interact with things on a very small scale down to the atomic scale. So we're also sensitive to some properties like magnetic spin of particles in materials, or thermal properties like vibrational modes in materials. But they're also penetrating. So they actually, like a microscope, you might put a very thin sample in front. You're not limited that way with a neutron beam, so it actually can go deep into materials like an X-ray can. in some sense, the opposite of an X-ray. So an X-ray gets blocked by heavier materials, so it doesn't see your skin and your muscles. It sees your bones. If you have any metal inside your body, it sees that really well. Neutrons are a little bit the opposite, so they're more sensitive to lighter things like hydrogen, and water is 2/3 hydrogen, so they can see water really well. So this is just a little example. This was not made at, this video is not from the SNS, but it is, oops, it is from another accelerator-driven neutron source, showing a mocha pot, a type of coffee percolator, doing its job in the path of a neutron imaging system. So that's all water in the bottom there, and you'll see it start to boil, percolate up through the central stem, go through the coffee, and then end up as coffee in that top container. So you can see the metal is basically transparent, and the water is very clearly imaged. The neutrons don't go through the water hardly at all. So that's not a good example of the atomic scale stuff. A mocha pot is much bigger than an atom. This is my last content slide. This is showing you all the different neutron beamlines we have in our target hall. There's a lot of them. There's 19 of them, and this isn't even counting the beamlines that we have down at the reactor. We're opening up a 20th one, so next year we'll be running with 20 beamlines. It's very exciting. The reason we have so many beamlines and not just one is, while you can imagine you can run multiple experiments in parallel, so every beamline can be running a separate experiment with a different set of users and a different question that they're researching, but each one's also tuned to specific types of questions. So you can use a variety of different materials that can be under study. So, you know, we do metals and crystal structures and biomaterials and polymers, and some of this is used for understanding properties from different manufactured materials. Each beamline consists of a sample environment, which is tailored to the kind of questions. So we can have high pressure, low pressure. We can put it in a magnetic field or not have it in a magnetic field. Some of them are high temperature, some of them are low temperature, some of them are room temperature. Some of them do small samples, some of them only take, some of them do bigger samples, some take powders, some only take solid samples. So there's just a variety of different ways you can configure this beamline experimental area, and then also a variety of different ways you want to detect the neutrons after they interact with the sample. So each of these is specialized for a different type of research question. And that's pretty much all I wanted to say about the SNS. This is a picture of me working on my small accelerator that's not the SNS, but is next to it. And I know it's a lot to look at. Here's a little cartoon of the visitor's perception of the accelerator facility. There's lots of cables. If it reassures you, I couldn't even tell you what exactly everything in this picture is doing and what every cable is doing, which is kind of one of the cool things about working at the SNS, is that everyone gets to be an expert in their area, but it's such a complex facility that you need everyone. So kind of like the parable of the blind men with the elephants. In this case, it's actually impossible for one person to know all of it. So you have to lean on your colleagues who have their own expertise in a particular area to really get anything done. So I think I've taken my share of time. I'll leave it at that.
All right, awesome. Thank you so much. Are there questions? I guess just to kind of get the ball rolling, I had a question. So I'm more familiar with accelerators that accelerate protons, which I know is what you do at the beginning, but I guess I'm wondering why you guys are interested in neutrons and not protons at the very end.
I'll preface this by saying I'm not a neutron scientist, but the way they interact with materials is just very different from the way a proton would. And I think a key to that would be the non-destructive aspect of it. I wouldn't send this whole proton beam on anything. Well, we have a powerful proton beam because we need to go through the target. But you're just going to interact differently. A neutron is a neutral particle. So its interaction with the nucleus is going to be very different than what a proton does.
Gotcha. I guess another one that popped in my head is, right, you have your circular part and then it's protons at that point. And so those are charged. And I know that when charged things go in a circle, they lose energy. So how much energy is lost as the protons are, because you said they go around like 1,000 times. And so like, how do you balance, losing energy with gaining energy too?
Yeah, 1,000 times isn't that many times, I'll say first. So collider facility, like the Large Hadron Collider or something, you're storing beam all day. So that energy loss per turn becomes a bigger question. So that's actually a pretty negligible effect for us. That's a much larger effect for electrons. So the radiation that comes off because of bending is going to be much more limiting with electron beams. So there is some, it's so small that we really don't have to worry about it here.
Mm-hmm.
But good question, because for some machines that is really important.
Right. Yeah, I guess when you're traveling at the speed of light, going around in a circle 1,000 times really doesn't take very long, does it?
No, it doesn't. I mean, we're someone told me the actual amount of time it was. It's not long. I mean, we're every 60 times per second, we're going through this whole thing again. So we're going through through the LINAC 1,000 times around the ring to the target, and 1/60th of a second later, do it again. So it's pretty quick time scales.
Are there any other questions for Kirsten? I guess if some pop in your head, feel free to put them in chat and we'll have some Q&A at the end. I guess if there aren't any other questions, then I think we should move on to our second speaker. Thank you very much, Kirsten. And now our second speaker is Shea Mosby from Los Alamos National Lab in New Mexico. He earned a BS in physics from Westmont College in 2007 and received a PhD in nuclear physics from Michigan State University in 2011, where he studied the nuclear structure of neutron unbound nuclei using fast neutron spectroscopy. He then joined LANCE, which is the accelerator at Los Alamos. LANCE is the Division of Nuclear Science Group, as a postdoc to study neutron capture using DANCE, the Detector for Advanced Neutron Capture Experiments. He became a permanent staff member in 2014 and the project leader for nuclear physics within the NNSA's Office of Experimental Sciences in 2019. He's also received a Presidential Early Career Award for scientists and engineers for his work on neutron capture and fission. And in 2020, he became a deputy group leader of the physics division's LANCE Weapons Physics Group. And in 2022, became the science liaison for the LANCE Modernization Project as part of the Los Alamos Accelerator Strategy Office. His current role is to coordinate with the LANCE experimental community to construct and advocate for the long-term science missions of the facility. In his free time, if you can imagine he has any, Shea likes to enjoys hiking, trail running, backpacking, skiing, and gaming. He has an agreement with his children that he will chase them anywhere, and they particularly enjoy challenging him on the ski hill. His wife is a triathlete, and he makes a game of seeing how many locations he can get a photo of her while on course. So let's thank Shea for being here, and Shea, take it away.
Thanks. My audio working good?
Yes, and I can see your slides.
Excellent. Just wanted to check. So thanks for the introduction. I'm going to talk to you about something that looks actually on the surface pretty similar to the SNS. And so I'm going to spend very little time talking about how the accelerator works, because you've actually more or less heard everything you need to know, and focus more on what do we do with this thing. So we're going to begin with this picture here, which is a photograph, an aerial photograph of the whole facility. And I'm going to point out a couple of things that are similar and a couple of things that are different to what you saw in the SNS. At the core of it, it's actually pretty similar. This long set of warehouse looking things is the linear accelerator itself. The main difference between it's less powerful and about 40 years older than the SNS accelerator first coming online in 1972. The focus of this facility is actually the thing that really differentiates it from the SNS, where accelerators are basically very, very powerful instruments that, because of the expense, are tailored to solve a problem, okay? And so what you were seeing at the SNS is we really wanted to have neutron beams to focus on material science, full stop. This machine has a broad focus, and that's going to be one of the two themes really of this talk. And so we're going to walk around here and look at the various end stations. So we start here at the lower end of the picture, and we're looking down the machine. And we actually put together both H plus and H minus beams simultaneously because of this broad focus, okay? We take the H plus beam and we send all of it to this first beam spur here at the lower left end of the picture, which is IPF, the isotope production facility. The idea here is you're working with the proton beam directly to slam into materials and breed radioisotopes that are used for medical, for example, cardiac imaging, cancer therapy, or research purposes. So that's one whole piece of the beam there. We peel this off at only 100 MeV, so a pretty small fraction of the total beam energy, more than an order of magnitude less than what you were hearing about with the SNS, but that is tailored to what IPF wants. The rest of the beam, which right now the way we operate is that H minus that you were hearing about that the SNS runs, continues all the way to the top end of this picture where we get to 800 MeV, which is a little bit less than the SNS. From here, we have what's called the switch yard. So we're generating 120 beam pulses per second, and we're sending them to all these other things that I have labeled with individual beam pulses that are tailored to the particular physics that each end station is going after. So we're just going to start on the left here where PRAD, proton radiography. Turns out we're a national security laboratory at our core. And it turns out that when you're in the game of national security, you care a lot about how things blow up. And so more or less, PRAD is the science of how things blow up. And I'll tell you a little bit more about it in a couple of slides. Here we're again working with the proton beam directly, and we're using it to do a very specific kind of fast imaging that I'll show you some data in a couple of slides. The next facility over is this warehouse looking thing in the top corner of the picture, where you're looking at our ultra cold neutron facility. Here is one of our fundamental science end stations. The idea is we're using the protons to make neutrons, much like you heard about in the SNS talk, but in this case, we're very specifically cooling them down to be moving very, 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 very slowly. And we use this for a class of fundamental physics experiments that at a high level are basically trying to break our understanding about how the universe works. So that's the first two. The rest of the beam we take across the road to the south side, where we hit a set of two different neutron spallation targets. So the Lujan Center is a slow neutron target, which means we take the protons, we use spallation as you've already heard about, and we slow the neutrons down to do a combination of mostly material science. So that's going to be very similar to what the SNS is doing, and then a set of nuclear physics. The nuclear physics also happens at our fast neutron facility, which is called WNR. The reason that we're doing nuclear physics for NNSA is more or less at a high level when you're looking at weapons. Nuclear weapons use nuclear reactions to burn nuclear fuel. And so it turns out, therefore, you have to have an understanding of the relevant nuclear reactions, and these facilities are tailored to go after that. Okay, so a lot of different things going on, two different beam species, 120 beam pulses per second, running all of these different facilities simultaneously. So the focus is large as opposed to being really, really good at a narrower set of physics. And then that brings me to the other bit of a theme that I want to have in this talk, which is the importance of people, okay? And so we already established we're going after a broad set of challenges, right? And the other piece I want to bring in at this phase is because of the national security focus, one of the things that we're particularly interested in doing is working on materials, components, whatever, that other facilities don't want to touch because of the challenges associated with them. So you're talking toxic, radioactive, explosive, classified parts where you have security concerns, that sort of thing. So you bring in the broad focus, you bring in the try and do really hard things, and the only way that you get to do it is you have to have a lot of really good people. Okay, so I'm going to revisit this at the end of the talk and give you a very quick vignette of the kinds of skill sets that are needed to make this place run. But this is more or less the reason that I decided to spend my career at the place is you have people that are good at all of these different things. They're all co-located. And so when a new question comes up where all of a sudden someone asks, hey, here is an issue that no one knows how to address, you more or less can walk down the mesa, staple together a half a dozen people, drag them into an office, and 2 hours later, you have your first sketch of a solution. In point of fact, I was in a meeting just like this yesterday afternoon. And so the punchline is that it's impossible to be bored because there's always something going on with so many different pieces of physics and accelerator science going on around the Mesa. So now let's go a little bit deeper into the way that each of these end station works. Here we go. I want to play this movie as well. So we're circling back to PRAD, right? Science of blowing things up. Cool. What does that actually mean? What it means is either we want to do something like this top little movie that I'm showing you, where the game is to make a movie. And what you're doing in this case is you are smacking a piece of copper with a shock wave from the bottom, and you've intentionally cut some grooves into it, and you're watching how those grooves elongate over time. By over time, what I mean is timescales between these frames that are smaller than a millionth of a second. So very, very, very fast. All right. The way that these things elongate tells us something about how copper behaves when you blow it up. So that's the game. The other game is to look at how high explosives work, which is this bottom video. And so what you're looking at here is we detonated this HE in 4 places, and you're watching the burn fronts and shock waves all come together. You're exploring what's happening on those edges. How do they collide? How do you smash the material in the middle of it? These kinds of questions. And so the reason that we're interested in using the protons and the reason that we're interested in using the accelerator is the fast protons can be bent with magnets. It's just like the lenses in your camera, okay? But they go through stuff. And it turns out no one is willing to let me blow up a pile of HE right next to a particle accelerator and therefore blow up a piece of the accelerator. So it turns out there's stuff I have to put around the HE in order to do this experiment to protect myself from it, okay? And so what I can do with the protons is I shoot them through, and I have my magnetic lens that lets me look and make these really cool videos of exactly what I want to see and ignore all the other stuff that's in the way that's necessary to let me do the experiment. All right, that's why you want the fast protons. The reason that we want the accelerator is I already mentioned its flexibility. Right, if I'm studying this time-dependent behavior, how does this evolve over time? I need to be able to make each one of these pictures when I want it and not otherwise. And so I can turn the beam on and say, I want protons right here, not there, right here, not there, and that sort of thing. So that's the basics of PRAD. To say a little bit more about what we do in materials science, which you saw a little bit in the last talk, at the Lujan Center, we're basically doing the same kind of stuff that's going on at the SNS. Let me get my laser pointer back. But we're focused on things that are interesting to national security. So the real focus is on this classified toxic, explosive, radioactive, this nasty stuff, okay? But again, you're more or less trying to understand material behaviors to make it easier for people that are trying to make a new part for some application somewhere to decide what material they want to use. And so you could imagine living in a world where I have 24 candidate materials to replace the case on the outside of my MacBook Pro because it's just kind of boring aluminum right now and maybe I want it stronger or lighter or whatever. One way to figure out whether or not it's going to hold up is to make 24 MacBook Pros with the candidate materials, drop them on a piece of concrete to see if they're going to hold up. And that's a very expensive way to figure out whether or not your material is going to work. The thing that we do with the neutrons is we take advantage of the fact that they're basically a microscope. And so we understand little samples of material. What does the microstructure, what does the material look like? And use that to predict how it's going to behave. And so of those 24, maybe you cut out half of them that you have to prototype. Maybe you do better. And so that's the idea, is you're helping people make decisions is the ultimate game. The other thing that you can do with neutrons that I find particularly interesting is this picture on the right here, which gets into nuclear energy space. So we already established that X-rays and neutrons interact with matter very differently. The very short version of this is X-rays interact with atoms, neutrons interact with an atomic nucleus, okay? Because of that, and because of the fact that the nuclear interaction is very, very different, we can get cool pictures like what we're seeing here. What we're looking at is a fuel rod, all right? So this is something that you would imagine putting in a nuclear reactor, and the X-ray picture looks like this column here where it's very boring, right? It looks like a stack of cylinders, cool. Things get interesting when you look at the right 2 columns, which is now we're taking advantage of the fact that the neutrons interact with matter in a very unique way. And what this means is every element interacts differently, every isotope of every element reacts differently. And that means I can have very, very sensitive studies of what particular part has what particular element in it, right? And so if I take a picture selecting onto uranium, I get this fairly boring picture. Good, there's uranium everywhere in my fuel pellet. That's what I want, right? If I go and I look, where is the tungsten? I get this blotchy picture. And what that means is that it's not uniform. It means that it's migrating and hanging out in very specific places. And so if I'm going to have a fuel rod that's going to sit in a reactor for a long time, and it's going to burn with nuclear fission, and that's going to breed fission fragments, other elements, by just burning the fuel, things like this come into the design and how you account for the fuel pellet design and safety considerations. Because if I'm making bubbles of certain nasty things that might pop and break the containment of this pellet, I need to know that. Okay, and so that's a thing that you can get out of the neutron beams. Moving on to the WNR facility, we already talked about the general need for nuclear physics. What it looks like in detector space, I show here as one example. So one of the things that we've been working on for the last 10 years is the outputs from neutron-induced fission. So the fission process is where you hit something like uranium, plutonium with a neutron, it blows it up and releases a whole ton of energy. This is more or less how a nuclear reactor works. And so one of the questions you can ask is, of all the stuff coming out when you blow it up, some of that's neutrons. How fast are they going? Turns out this is really useful for understanding and making predictions of next generation reactor performance. So we did the experiment here, where in the middle, you have something that fissions, so your little pile of uranium or plutonium, and around it, you have detectors that are looking for those outgoing neutrons. And then you count. You turn on the neutron beam, induce the fission, look for stuff. That has a number of different applications that we can talk about in Q&A if people are interested. But the other thing you can do with the fast neutrons is keep harping on that game of neutrons interact very differently than any other probe. And so here, I'm showing you a picture, bottom right, of we stuck a rose inside a lead can that was more than an inch thick. Okay, so more or less any x-rays or anything like that ain't gonna penetrate. You're just gonna see the outside can. The neutrons actually penetrate this hugely thick can and then can tell you, hey, look, there's a rose inside. Once again, that's giving you an idea of why you're interested in using the neutrons as opposed to something else. And so we do both of these kinds of things at this facility, exploiting the fast neutrons for a combination of the nuclear physics experiments, so understanding nuclear reactions, and then more neutron imaging applications. So the last thing that we do at the WNR facility is radiation effects. So this gets into the fact that we are more or less bathed in a constant source of radiation all the time. It depends on where we are on the planet. So the particular problem that we're trying to solve here is cosmic ray neutrons, or to give you a very particular example, if I'm on an airliner, right, at a high elevation, and all these modern aircraft are fly-by-wire systems, which means you're more or less flying the aircraft with a computer, I care a lot whether or not cosmic ray neutrons that are the result of high energy particles coming from the sun or from outside the galaxy, whatever, hitting the upper atmosphere, making neutrons, streaming in, damaging the electronics, and then causing the fly-by-wire system to fail. Okay, that's the kind of problem that you're worried about. And so we get a lot of different industrial partners. I show a list here. You might recognize some of the names that worry about this kind of thing. All right, do my electrons hold, or my electronics hold up? The reason that we do the tests here is this plot. Yes, I know I'm showing you a plot. On this axis, we're looking at how many neutrons there are. Okay, y-axis, how many neutrons, and the x-axis is how fast they're going. And the blue and the red lines are showing you what does this cosmic neutron spectrum look like. So how fast are the neutrons that are coming down from the upper atmosphere, and what our facility can produce. And more or less the lines overlap each other reasonably well, which means we can simulate these effects and look for electronics failures. Okay, so that's what we do. And you do it in fly-by-wire systems. You can imagine that you care about whether or not your iPhone keeps working after a plane ride, these kinds of questions. We already mentioned a little bit about IPF, and I just said the words cardiac imaging and therapy. So let's look at this little picture here, bottom right, to talk more about the therapy side. The idea is I can make radioactive material. If I can attach that radioactive material like an alpha emitter, and I can put it in a molecule that specifically targets a cancer that I want to kill, I can then dose the cancer cells with radiation, kill them, and not harm the rest of the body, or at least not harm the rest of the body as much. And so the way that works in practice is I'm showing you a picture that's the result of our ongoing efforts in this actinium-225 project, where this leftmost picture is a guy that has dramatically metastasized cancer. Okay, so all this dark stuff in torso and everywhere else is metastasized cancer. So this individual, when he got into this particular test using actinium-225, there was no treatment options. The patient was terminal. After 3 treatments with this actinium that we can produce using our accelerator, you see that the patient is now clean, he's cancer-free, right? So that's the kind of thing that you're trying to do using these radioisotopes. Okay, our final end station that I'm going to say a couple of words about gets into this physics of trying to break our understanding of the universe, right? Making really, really cold neutrons and then conducting very specific experiments utilizing them. I'm showing here a little picture of what it looks like to make these cold neutrons, where you have the proton beam coming in, and all of these different colors are different materials that you're choosing to balance what I like to think of as a Goldilocks problem, okay? When I have a high energy proton beam, it comes in and makes a whole bunch of different neutrons that are all kinds of different energies. I need to make them all go really slow. And I need to make them all go really slow without eating all of them. So the favorite way of neutrons to get lost, to lose them, is they capture on something, which means they run into another atomic nucleus and they just stick there, okay? And so I have to say, okay, what materials are good at stealing energy from neutrons? And what materials are good at not absorbing neutrons? And then I build this heterogeneous mixture of all of them to try and buy my way down to the very particular neutrons that I'm interested in studying. And so there's a very high amount of overlap of physics and engineering that goes into making these specialized neutron spallation targets. It's kind of dealing with the proton beam power that you heard about in the last talk, but then also, what am I trying to get out of this thing? Okay, and that's again one of the things that keeps life interesting around here, because we run a number of different targets to get at different particular pieces of physics. So bringing it back to the people side, right? Because here's this broad spectrum of stuff that we're doing. And I'm going to walk you through in just a couple of minutes, what are the kinds of skill sets, kinds of interests that it takes to run a campus like this. Okay, so at a high level, number one, we have to operate a particle accelerator. If there's no beam, nothing else matters, right? And so for there, you need all kinds of stuff. You need people that operate the machine. You need the design and the engineering to do the custom fabrication of interfaces between the accelerator and whatever you're trying to couple into on the experiment side. You do need physics people to actually design new beamlines and understand what the machine itself is doing, because it's never a static thing. You need to make ions. You have to actually have control systems so you can actually make this thing work. You need vacuum systems. You need diagnostics to tell you where the beam is going. And this is just a subset of what you need. Okay, this is by no means exhaustive. And then you need to do all these really hard experiments that I've been harping on about, where you need somebody to say, what is the science that we're doing? That's not remotely sufficient. You have to have someone that says, okay, how am I going to measure the thing that you want to measure? How am I going to get those signals on a disk, right? Which involves, how do I couple detectors to electronics to signal processing, which involves a certain amount of electronics design and possibly software engineering. How do I analyze data? That really starts to get into software engineering. How do I assemble all of my experiments? Things like making all the parts, doing the chemistry on those radioactive isotopes, or sample environments, which is if I want to measure the material properties of something hazardous, but I want to bake it really, really hot and then smash the snot out of it, someone has to figure out how to put all those components together in a way that both keeps people safe and lets you do the physics, right? And then there's a whole set of folks that worry about, really focused on the safety and the security side of things writ large. So things like safety interlocks. We have to make sure that people can access the parts of the facility that beam is not being delivered to, but keep them out of everywhere the beam is being delivered, and different parts are running at different times, right? So this is a whole set of control systems that you have to design on both hardware and software sides, okay? And again, the list isn't exhaustive. The point that I actually want to make is that it's not just about PhD scientists, right? I have the title doctor, yippee, but it turns out the majority of folks working on this MESA, right? They're either high school education or an undergraduate degree, right? It's the minority that actually have advanced degrees. And so you need a broad set of people, personalities, and skill sets to put it together. The common thread is you want to be part of something cool, right? So with that in hand, let's transition. The last few minutes, I wanted to say a couple of things that I'm going to claim that I've learned throughout the course of my career, because maybe it'll be interesting to you. I think it's interesting. So we're going to walk in about 2 minutes through what I did and then say a couple of minutes of what I think was interesting about it for the past 15 more years. So back when dinosaurs ruled the earth, I was an undergrad at Westmont College. So this was in California. And my path was a little weird. In high school, I actually wanted to do history and came to the conclusion that, at least for my own brain, my own interests, that history was better as a hobby than as a profession, just because of the kinds of jobs that people actually are willing to pay you to do as a historian. And so I was decent at math, so I got into engineering. But because of opportunities to do summer research and go to a nuclear physics conference, by the time that I was in my 3rd year of undergraduate, I had switched to the full-on physics track with the intent to go to graduate school. So the opportunities were actually the key here. So I'm going to mention it again in a minute, but an important thing, if you get the opportunity to test drive something that you think would be interesting as a career, whether it's an internship, touring a facility, going to a conference, whatever, take that opportunity. You can learn a lot about whether or not you're going to find it interesting or not by just going and hanging out with people that actually do that thing as a living. In graduate school, I did this in experimental nuclear physics, and that has grad school has a couple of things that are interesting. One of which was got married in 2007, so between undergrad and graduate school. And so me and my wife were going through the program at the same time, me in nuclear physics, her in nuclear chemistry. And we had our first kid while both writing our dissertations, which makes for a very interesting life experience, being a full-time student and a full-time parent at the same time with a partner who is the same. So this has interesting consequences about why we ended up at LANL that I'll get to in a couple of minutes. And then at LANL, I wandered around a little bit, right? I was a physicist until 2019, so actually doing some of the experiments at Lance. Then I got into management for the basic reason that someone has to help run the place, otherwise it doesn't run. And I cared a lot that someone who was passionate about the science that's going on at the place was helping to run it, because you often have to make very complicated decisions that have real consequences. And so understanding what the impact of those is going to be is important. And then finally today, more or less, I'm worrying about how does Los Alamos National Lab within NNSA think about accelerators long-term, okay? And we continued, it turns out my spouse works at the laboratory, and so we continue to collaborate with each other, which actually helps make life pretty fun. So, okay, a couple of words on what I think I learned from all of that. One of which is, I told you the two-body problem and having a kid in grad school contributed to why we ended up at LANL. So this actually couples into this next set of bullets. When we had a kid, we both were doing school full-time and doing the parenting full-time because we were broke grad students. We didn't have money for childcare. And so when we were deciding, okay, where are we going out of graduate school, we had this conversation of who wanted to do what, okay, where there wasn't actually a preordained answer. And it happens that my wife was actually having a lot of fun hanging out with the kids. And so she made the decision, okay, I want to hang out with the kids for a couple of years. Maybe I want to end up going back into academic world, maybe not. And this is part of why we came to LANL, because the big lab at the time, it was 10,000 people, now it's significantly more, and it has a lot of overlap with nuclear physics and nuclear chemistry. And so I could get a job in one part of the laboratory. We could learn the lay of the land, learn the ecosystem, but we figured there would be a good chance that she would also be able to independently get a career going at the lab if she decided to. And turns out a couple of years later, she indeed decided that she wanted to do this, and now is off in a different part of the lab having a successful career. And so trying to figure out how are you working all these life choices out can have a significant impact on where you end up working for the rest of your career. The other piece I want to just re-emphasize is it was very, very, very important, the early experiences that I was able to get in going and doing some research, going to a particle accelerator and seeing how it works there, and seeing what the mentality of the people that are doing physics as opposed to engineering was, to figure out what my brain wanted to do. And so this could be hugely important to finding satisfaction in your career long term. And then the final thing that I want to mention is, yes, we're doing a lot of high octane stuff, right? I take my job pretty seriously, but if you're not having fun, that's going to make it hard to keep this up long term because it is actually challenging stuff that we're doing. And so a thing that I like to tell people is that I show up to work for the giggles, and that's more or less true. I actually really like the people that I get to work with and what I get to work on. Like I said, it's never going to let me be bored. But as a result, okay, we're going to end with a couple of silly pictures, right? You can't take life too seriously. I ski with a Viking helmet cover because it's silly. And my daughter had in this ski session, put on as many ridiculous things as she could to just make us laugh. And so she's a rainbow tiki hulacorn. And my wife still knows how to smile even when she's 5 hours into a triathlon. So that's what I got. Do you have any questions?
Awesome. Thank you so much. Any questions for Shay about life or having fun? I thought that was a really good point, is that, yeah, this should be fun. Life should be fun. So I guess, so if you were interested in working on an accelerator team and you didn't want to, say, go to graduate school, what can you do in college to kind of help get you on that career path?
Yep. So one of the things is talk to us. So, right, there's more than one of us that's online at one of these accelerators. So take advantage of the fact that you're part of this program and send some emails, because right, the way that you can interact with an accelerator facility in undergrad is vast, right? Like if you're trying to do things in an engineering program, there's places that we can couple you into that do engineering. If you're on a science track, there's research groups that you can get involved with. If you're in computer science, right, there's data processing, software engineering all over the place. It's kind of embedded in many different aspects of the place. And so frequently there are either official programs, things like REU, research experience for undergrads, or just getting directly hooked up with someone working at the place where they can find the funding, find the money to bring you out and hire you for the summer to go do a particular thing, so that they get something that they want, you get something that you want, which is experience, and everybody goes away happy. And so really it's having the will to go and reach out, take advantage of whatever means that you have of contacting people, and just talk to folks and figure out a way to get involved. I see there's something in the chat. So what is the best part of my job science-wise? So up to a couple of years ago, it was getting to do the cool experiments where I worked across both Lujan and WNR. If you come back here, this lower picture is me by our detector for advanced neutron capture experiments. And it was going and making those experiments happen because they're really hard. And the whole reason that you're doing experiments, so what I liked about experimental physics is the reason that you're doing it is you don't know the answer. And so you're kind of, I like to think of it as writing nature's answer key, right? And so the uncertainty where you're acting on incomplete information, you have to take your best shot and see what happens. And I found that to be exciting. Now, because I'm kind of worrying about the bigger picture, it's getting to talk to everybody from all over this mesa. So more or less, I have regular meetings with at least one person from each of these end stations and from the accelerator, and figuring out how to make the connections to plot a course long-term of where we need to be going, because none of these machines happen by accident, right? And so you're kind of worrying is a silly way of saying it. What you're trying to do is gain a perspective on where am I trying to get in 10 years and 15 years, and what things am I putting in motion now to get there, right? Because these things are complicated. And so it's, at this point, the thing that I enjoy the most is just talking to people, seeing what the ideas are, and trying to staple them together to get us somewhere cool and interesting next.
Great question. Any other questions? If not, I actually was thinking that it might be interesting for both Shay and Kirsten to just talk about, like, what's your typical day like from, getting into the office and then leaving to go home?
I've been talking a lot. Kirsten, you want to go first?
Yeah, say give your voice a rest for a second. Yeah, so typical day. It really depends on whether my beamline is running or not. So a typical day could be I go in, Usually have a couple meetings. My group is very good about socializing, so there's always one coffee hour for half an hour. We all sit down and just talk to each other socially or about work things, but always with coffee. So make that if I can, sometimes running computer simulations or doing data analysis, and then meeting with other people who are working on my project. So that's what it's been looking like recently, because my experiment is offline. When it's running, some days can look like, get it in as early as I can manage, start something that I know is going to take a long amount of time, and try to fit it into a day, or arrange with the accelerator operators to let it run overnight. So some days can be all about just getting the data, less time from talking to other people. So that's where I'm at these days.
So back when I was doing science, there was more parallels to what you just heard, where it's start something that you think is going to take a while, that sort of thing, where there was less meetings and more sitting at my computer or down at the experimental station doing a thing. One of the interesting features of the Mesa here being so geographically dispersed, and so the accelerator itself is a little bit more than a half a mile long, right? So things are actually fairly far apart. Is there was a day back when I was a scientist where I was bringing up 6 experiments in one day. And so I showed up to work in running clothes and spent the day just jogging around, because that was the most efficient way of trying to get from place to place to place. That doesn't happen every day, but it was noteworthy and it was very interesting. These days, more or less, it's a combination of getting in and taking stock of, okay, who am I talking to today, and finding time when I'm going to think about all of this stapling things together that I'm talking about, because the stuff that I'm usually delivering, so like when you're a scientist, typically the summation of your work is like a peer-reviewed journal article where you write everything down and you submit it, and things go forward. Mostly I write reports and presentations, as in briefings to people who can make decisions and figure out where money's going to go, or documents to back the same things up. And so it's a combination of talking to people, working on that inherently more squishy stuff, and then usually trying to schedule some time, like officially putting it on my calendar, blocking it out, of locking myself in an office just to stare at a wall and think, because there's a certain amount of just thinking that you need to do to keep up with this stuff.
Yeah, I will say, I think if you form your idea of what a scientist is based on, popular culture, watching a lot of Big Bang Theory, you might think this is a great job for me. I'm just gonna like sit in my office, close my door, block people out all day, which there is times when you have to do that, but man, I talk to a lot of people. It's a very social job, especially at these big facilities. You have to know what's going on. You have to ask people nicely to help you out with something, and yeah, there's a lot of room to be social, and communicating stuff to other people and being good at public speaking, and all of those skills are actually way more important than TV media led me to believe.
Yeah, it's hard to overemphasize the extent to which modern science at this scale is collaborative. Like, you just can't do things with this kind of science anyway on a benchtop on your own anymore. That's just reinforcing what you just heard.
Yeah, I absolutely agree. Those are good points. We do have a question in chat. How do you achieve a good work-life balance as a scientist?
You want to go first since I've been talking again? I feel like I should just give you dibs on every question.
Sure. I don't know. Shay has the experience of balancing kids and science. So me and my husband about to have our first kid in about a month here. So we'll report back to you how that goes. But I'm also part of a 2-body problem. So Shay explained his situation. So both me and my husband work at Oak Ridge National Lab. And I mean, I think part of getting the good work-life balance is I found that the workplace at the lab is very open to flexibility. So the place where I work is not very rigid with these are the hours you must work. So this is both a good and a bad thing. It's good. You can take time off in the middle of the day, go to your doctor's appointment, I'm sure this will be very helpful with having kids and working around their needs and their schedules. But at the same time, it's metering yourself and not burning out, because you can work for 12 hours a day on your experiment if you want to, and if you feel that internal pressure to perform. So it's kind of learning how to run the marathon and not the sprint once you're out of school and you're settling into a career. But I think in general, the labs are good about offering that type of flexibility to have a good balance. I don't know if that's been your experience at Los Alamos.
Yeah, it does, depending on exactly what your life situation is. Around where I work, it can guide you to make some detailed choices of exactly what you want to work on. So like one of the things I take advantage of right now in my current gig is we have 2 kids and my wife and I both work. Because of what she works on, she has to be on site a lot more, as in she has to talk to people, but talk to people in an environment that you can't be talking remotely. Okay, so she has to go to a special building and that sort of stuff. And so one of the things that I'm able to do at the bookends of the day is like I can do a little bit of work from downstairs at my home and then get kids off to school and then actually go on site and start my in-person meetings and whatever else I got to do on site. And so you can balance that and turn that knob a little bit depending on what exactly you're working on. So that's one thing. The other thing that I was going to mention is, oh yes, the sprint versus a marathon thing is highly, highly important. And so one of the things that was, and let me back up. What you have to do is you have to actually just own it, right? Because mostly because the working hours themselves aren't really tracked so religiously, what you actually get seen for is your productivity. Okay, that has 2 consequences. One of which is there are people that can spend 60 hours a week on site. I actually saw this a lot in graduate school where there were other grad students that spent 60 hours a week on site. But you spend an hour and a half a day having coffee and working your way down the hall and just chatting with everyone. And that's a choice, right? Or what I was doing was I actually worked closer to 45 hours a week during grad school and got out in 4 years, which was reasonably quickly for my program. Because when I was at work, okay? As in focused on what's the task at hand and just figuring out how to be rigorous during the day. And so you can, again, this is a knob that you can turn up and down because some people actually more or less like their whole social life is at work because they really like the people that they're working with. And then some folks, okay, because of life situations or whatever, it's just not the case. So that's a thing that you should be cognizant of and figure out where you want to live, because there's not a rubber stamped, this is the way everybody has to do it, right? That's kind of one of the points you're seeing here is there's a number of different ways to make this work well. And then it's managing the expectations of the folks that you work with. So there are folks that have authority that will take just as many hours per week, month, year as you're willing to give them, right? And they will either try to excite you into getting that or browbeat you into doing it or whatever, right? Because there's a whole mix of different personalities that are interacting when you're at such a big place. And so one of the adulting aspects of this is to say, no, I'm making these choices. They are worthy. I'm getting my job done. I'm performing, but I draw the line here. I'm not going to come in on this Saturday night if it's not actually an emergency just because it's fun. Right. And these are choices that you can make. And the important thing is to own whatever it is and tweak it to whatever career path that you're trying to actually achieve. At least that's how I see it.
All right, great answers. We have another question in chat. Lois says that she really liked the cancer research application, found that fascinating. And so do you have any other sort of examples that high school students could relate to of science you can do?
Yeah, so if you get back to what was going on with IPF, let's just stay in that space for a minute, if I can figure out how to scroll the right direction here. Right, so I mentioned but didn't say anything more about what goes on with medical imaging, right? And so if you're doing something like getting a CT scan, one of the things that you might be doing, particularly if you're getting older like I am, is you care about whether or not your heart's working. And so one of the things that was a major product of IPF for a long, long time was strontium-82, which is used for cardiac imaging. Basically, you can bind it to a molecule that is good at getting sucked up into your bloodstream and then hanging out near your heart. And you can see whether or not everything is working right, as in is all the blood flow doing sensible things. Okay. And that's again a case where the idea was you were trying to make something that would give off gamma rays in relatively low doses, as opposed to the actinium, which is giving you alpha particles. Don't worry about it, it's just jargon. It's different forms of radiation that have different properties. Okay. And so the properties of the strontium that I'm talking about were it was good at giving off radiation that would penetrate out of you and then get seen by detectors that can tell where the radiation is coming from and then tell you whether or not your heart's working right. Okay. Those are so you have the therapy side that we already talked about, and then you have the kind of imaging side that now you've heard about. So that's kind of the leading example that I would give in this IPF land. And I guess question back to you was, were you interested in like this radioisotope stuff, or were you interested across the whole science program of the whole MESA?
I guess maybe while Loy's probably typing, what about the whole MESA?
So whole MESA, one of the things that we do at the Lujan Center, and I imagine this actually has significant overlap with stuff that goes on at the SNS, was an experiment that we did to understand bridges. Okay, so like, let's say I'm on the Brooklyn Bridge, right, and I have all these bundles of steel cables. And the bridge was originally designed with, I don't even remember what it is now, it was like a 30 or 50 year life expectancy, and we're way, way beyond that by like a factor. And so there's two different questions that you could ask about this old bridge. One of the questions that you can ask is, at what point are we worried about it just falling apart, just as it gets old? And another question that you can ask yourself in the modern environment that people did start asking after 9/11 was, what happens if someone tries to damage the bridge intentionally? Okay, this is actually the specific question that we got involved with, which was, the question was, if someone lights a tanker truck on fire on this bridge, at what point are these bundles of steel cables going to structurally fail? Okay, or put differently, how much abuse can you subject a bridge to before it starts structurally failing? And so what we're able to do using these techniques of using neutrons as microscopes is we built a fake bundle of cables and stuck it inside our instrument and started making it hot and then pulling on it. Okay, and then you start seeing, okay, as you crank up the temperature, when's it falling apart? That's thing one. And thing two is, to get to some of the aging stuff, we started taking the cable bundle and then intentionally introducing damage. So clipping different pieces and then watching with the neutrons, how does the stress on the cable then transfer to other cables in the bundle? Which, that kind of sounds like a trivial question, but it's actually really, really, really not, because all of these cables are kind of stuck together. And so they all have friction against each other. And so it's not really, when you clip one, it's not such a clean thing as just turning it off, right? There's actually a more complex interaction. And so there's a fair amount of engineering studies like that that amount to, how much can I abuse part X? Okay. We already talked about some of the imaging stuff, like with this nuclear energy that matters for fast reactor design. The other thing that I'll just mention at a high level, I don't have any pictures of it, is on the nuclear physics side. As we're looking to get off of fossil fuels, right? There's a whole number of different technologies that we're trying to use to get off of carbon and ultimately get more green, okay? And in that space, one of the attractive components is looking at next generation nuclear reactors, okay, that make less waste, burn more efficiently, use less nasty nuclear fuels, okay? In order to get a good understanding of how those things are going to work, which really comes down to how much money are you going to have to spend prototyping and getting certified to actually run the thing safely, right? You're very dependent on your calculations. And so there's a certain amount of nuclear physics work we do here looking at nuclear reactions that people didn't care about 40 years ago, but are highly relevant to new reactors. So one of them is chlorine. Turns out chlorine will show up in some of your salt type advanced reactor systems, and it can eat neutrons. And so if you're worried about whether or not you're going to make energy or just have something fizzle, you really want to understand how chlorine eats neutrons. And so in point of fact, over the last 2 years, we've been doing experiments to specifically understand how does chlorine eat neutrons. So there's a couple of more.
All right, and we have one last question. This one's for Kirsten. Thank you, Shay, for hearing about your career path. Kirsten, can you maybe talk a little bit about how you determined your college major and career path, and what / who influenced you the most?
Yeah, I actually have a couple pictures. I'm gonna, oh, Shay, you have to stop your share.
Let me get off. There you go.
Okay, now I can take it. Yeah, so I guess I decided on physics as a major pretty early in school. So I had a really good physics teacher in high school, and came into pretty early in undergrad, said like, all right, I'll do physics. These classes are really fun. I really like them. I first discovered the field of accelerator physics in undergrad. So this is a picture. This is a much smaller particle accelerator than the SNS. So it's sort of in the middle of this group here. This is called a cyclotron. It's a single magnet, and then there's a little vacuum chamber sort of pancaked in the middle there. That's the actual where you do the acceleration of particles. And this actually wasn't my doing. So this is me standing between my two lab partners. So the guy in the brown shirt was just super nosy, like couldn't get him away from anything. He wanted to know what everything was. So this was sitting in the back of our laboratory classroom where we were doing lots of, pre-set up physics experiments as part of coursework. But he wanted to know what this thing was. And it turns out it was a small accelerator project, and we got to do an independent study on it, mentored by these two. So this guy in the black shirt eventually became my PhD advisor, because I thought this accelerator thing is really interesting. Let me keep going with that. And this guy in the red shirt eventually became my husband. So it's a pretty good lab project. Worked out really well. More pictures of the cyclotron and us doing magnetic field measurements in the plane of the magnet where you do the acceleration. Went to graduate school, worked on an accelerator there, slightly bigger, still a lot smaller than the SNS. So this was a small electron ring at the University of Maryland. That's the whole accelerator. It's just a little ring. And that's our little control room on the left with me and a graduate school colleague. So that's how I got started, a nosy lab partner, and then I just kept doing it. I was really drawn to the applied side of things. So just the idea that not only are you doing the physics and you're doing the physics calculations and you're running the simulations on your computer, but you're also going down to the lab and taking measurements and influencing some of the hardware that's going on the small accelerator. And these two small accelerators were great because it was so hands-on, right? Like literally there's our hands on the machine, installing an iron piece to shape the magnetic field. So really got to bridge the gap between the engineering and the machining of things, and then also the physics and understanding how particles move and get accelerated by these fields. So I like that aspect of it, as well as just knowing that your work is going somewhere good. Like accelerator facilities, are driving these programs that I talked about, that Shay talked about. Every accelerator has a mission, whether it's fundamental science or material science or, energy sciences. And so no matter what facility you end up working at, it's all going for a good cause. So that was also important. So that's pretty much this is just my current facility. Lots more complicated pictures of accelerators, but being able to just continue it, I graduated to a slightly bigger accelerator. But still motivated by those small hands-on experiments that I started with.
All right, great. Well, we are at the end of our allotted time. So I was going to hand this back off to Daniela to sign out.
Yes. Thank you so much. for your talk. I really enjoyed them. Thank you so much for being here today. I just want to say that this is the first part of 2 Sage Live events. Next Sage Live will be next Saturday. So if you can please join us, Cindy Joy from Fermilab and Matt Gibbs from Slack National Lab will be here next Saturday at the same time. So I'll be sending the email invite shortly. So it will be great to see you. And thank you again so much, everyone, for joining us today. I'll stop the recording somehow.